Here I've listed a set of steps that you can think through for most limits. The first question you should ask is if it's a piecewise function. If it is piecewise, you need to check each side separately. If the two-side limits agree, then the common answer that they share, that's the limit. And you always ignore the point where x equals c. If you are taking a limit of a formula, typically you look at the formula and decide, does it look like it's a continuous formula? Every algebraic formula that we see is continuous. If you can plug it in and the number makes sense, it will be continuous. And so when it's continuous, the third step, we just use the value we get when we plug it in. On the other hand, if it's not continuous, then we need to ask ourselves in what sense. So it might be 0 divided by 0 or infinity divided by infinity. These are examples of indeterminate limit forms. We cannot answer the question based on the form it's in, so your task is to rewrite in a new form. We often use factoring to do that, and then we start over. If the limit form is infinite, so we get a number divided by 0, or a number times infinity, then this is not indeterminate. We have an infinite limit. We need to do sign analysis to decide the values on either side. So here's our first example. I want to take a limit of the function x cubed minus 10x plus 3 divided by x squared minus 2x minus 3, and I want to do that as x approaches 3. This is not a piecewise function, so our first step is simply to try plugging it in. When we plug it in, we get 3 cubed minus 10 times 3 plus 3 on the top, and on the bottom we get 3 squared minus 2 times 3 minus 3. In both cases, I get 0 over 0. I want to compare that to the graph I've shown on the right. The graph on the right shows the graphs of x cubed minus 10x plus 3 in purple and x squared minus 2x minus 3 in red. The key observation is that at x equals 3, both graphs go through the origin. And so I have a 0 over 0 form. When you have an indeterminate form, our job is to rewrite it. We need to find a new formula. The way that we'll do this is through factoring. I find it easiest when I have a 0 over 0 form to use synthetic division to factor out our x minus c. So here we're going to factor out x minus 3. Our coefficients for x cubed plus 0x squared minus 10x plus 3 divided by x minus 3, which has a root at 3, so that's our number. We do synthetic division, adding when we do vertical steps, multiplying when we do diagonal steps. And so we find that our remainder is 0. We should have predicted that based on our formula. And the 1, 3, minus 1 are our coefficients of our quotient. We will now do a similar factoring of x squared minus 2x minus 3. The coefficients of x squared minus 2x minus 3 divided by x minus 3, a root at 3. Again, we have a remainder of 0, and we have the coefficients of our other factor. This factoring allows us to rewrite our limit using our factored form. The coefficients of our numerator, second factor, were 1, 3, and negative 1. The coefficients of our denominator, second factor, are 1 and 1. The common factor of x minus 3 cancels, so that I get a new form for my limit. Take the limit of x squared plus 3x minus 1 divided by x plus 1 as x approaches 3, and this is a form that's determinate. We can find the answer by plugging it in. 3 squared plus 3 times 3 minus 1 all over 3 plus 1. We get a value of 17/4. My second problem uses the same formula, but this time we're going to let x approach -1. And I had a typo there, so let me make that clear. X approaches -1. So this time if I plug in x approaches -1 into my formula, on the top I get -1 cubed minus 10 times -1 plus 3 all over -1 squared minus 2 times -1 minus 3. On the top, my formula goes to the value 12. On the bottom, my formula goes to the value 0. This is not indeterminate. Because I have a number divided by 0, this is the form of a vertical asymptote. Again, we can see this in the graph. So here's x equals -1. The numerator has a value of 12, while the denominator has a value of 0. And so I'm taking a number that's very close to 12, dividing it by a number that's getting closer and closer to 0. And so a number like 12 divided by a very small number, it gets huge. So this is an infinite limit. Now on the previous problem, we already factored these two polynomials. So let me just write that down. And we want to find the value of the limit as x gets close to -1. Now, with the graphs on the side, it's actually fairly easy to figure out the value of the limit. If I look on the right-hand side, we can see that the numerator is getting close to 12, where the denominator is getting close to 0, but through negative numbers. The way we can represent that is we can write the limit as x approaches -1 from the right of my function has a limit form where the top is getting close to 12, the bottom is getting close to 0, but the way it's getting close to 0 are through negative numbers. 12 divided by a small negative number is a very large negative number. And so this limit is going to be going to -infinity. On the other hand, if I look at the right-hand side, we can see that the numerator is getting close to 12 again, but the denominator is close to 0, but positive values. The way that we can write that is we again do a one-sided limit. We say x is approaching -1 from the left of our function, and we get a limit form where the numerator is getting close to 12, the denominator is getting close to small positive numbers, and so 12 divided by a small positive number is a very large positive number, and our limit will be +infinity. So what do you do if you don't have a graph? Well, that's why we factor. Factoring allows us to do sign analysis. To do sign analysis, we need to find the roots, which we find by setting the numerator equal to 0. We get either x equals 3 or this quadratic x squared plus 3x minus 1 equals 0. We solve the second by using the quadratic formula. When we simplify that, we get x equals -3 plus or minus the square root of 13 all over 2. We need to know these decimal values so we can do a number line. The value on our left is -3.303 approximately. The value on our right is x equals positive 0.303 approximately. Those points that we found correspond to the 2 points on the graph where the purple curve crosses the axis. We also need to worry about our discontinuities, which we found by setting the denominator equal 0, x minus 3 times x plus 1 equals 0. Notice that we get x equals 3 from this, and x equals -1. Just a caution, because we found x equals 3 in our discontinuity, that means in fact it was not a root. And so when we do our sign analysis, we have at -1 a single discontinuity, undefined, at -3.303 303, we have a root. At positive 0.303, we have another root, and at x equals 3, we have another undefined point. At x equals 1, we have a vertical asymptote. The last problem showed that at x equals 3, we had a hole. We're interested in deciding what's happening to our function in the vicinity of our vertical asymptote. So we need to check the sign on either side. So we pick a number. We might pick x equals 0 on the right and x equals -2 on the left, and we can calculate the values. So if I plug x equals 0 into my formula, x minus 3 at 0 is negative. X squared plus 3x minus 1 at x equals 0 is negative. And so on the top, I get a positive number. The denominator, I have another negative number times a positive number. So on the bottom, I have a negative number. And so when x equals 0, on the top I had a positive number, on the bottom I had a negative number, so my overall sign is negative. If I now plug x equals -2 into my formula, plugging -2 in, I get a negative. On the quadratic, I still get a negative, and -2 makes that negative. So all four factors are negative. That means the sign on the left is positive. These signs are the signs that I use to calculate which infinity I actually had. So whether I have a graph or whether I use factors in sign analysis, I can determine the signs of my infinite limits in the case where I have a number divided by 0. For our final example, we look at a limit of a function that is piecewise. When a piecewise function appears, we need to take the limits of each side separately. We start by taking the limit on the left. X approaches 2 from the left. That means x is less than 2. And so we go up and look at our inequalities. When x is less than 2, our function uses the formula x squared. We will be taking the limit of x squared as x approaches 2. This is a nice continuous function, and so the answer is 2 squared, or 4. The limit on the left is 4. We now do the limit on the right. The limit on the right has x approaching 2 from the right of our function. This means that x is greater than 2. When we look at our original formula, x greater than 2, our function uses 2x minus 5. We take the limit of 2x minus 5. Again, this is a continuous function. We can just plug in our values and we get 2 times 2 minus 5 equals -1. The limit on the left and the limit on the right disagree. Because they disagree, we say that the limit of our function does not exist. I want to pay special attention to the fact that we never actually used the formula when x equals 2. If the two limits from our left and right limits happen to have both been 4, we would have written that the limit equals 4. If they'd both equaled -1, we would have said the limit of the function equals -1. But we never would have said the limit of our function equals 3, because a limit never looks at the actual point. It looks at the values coming from the sides.